All right, I think we can get started now. First, I want to thank everybody for taking the workshop yesterday, given by Richard. And the recording is already on YouTube. We have a channel. I'm going to copy and paste the channel here in a minute. And Metagena Foundation has a YouTube channel. We put our workshop information, a recording on the YouTube channel. And I also saw quite a few comments from the LinkedIn, and thank you, Richard, for the excellent workshop yesterday. Today, we're going to move to the second software tool we have, which is ESPEI. ESPEI is for CAFAD modeling, so to calculate, to evaluate the model parameters. I do want to mention that we have another paper come up with DFTK. We believe it's also ready for user as a user tool. So we're going to have that one probably rolled out sometime end of this year or early next year. I have a workshop on DFTK. It is how to calculate the free energy. Use DFT, use VASP, which you will see that it becomes very user-friendly. And that's the second one. The third one, we do have the fourth one coming up too, is machine learning. It's not a user tool yet, but we hope it will become user tool very soon. Hopefully by mid next year, we have have the machine learning code also rolled out. All of them integrate together with our database. So that means the database, from one database, you can get all the data for DFT calculations, get the data for the ESPEI modeling, then use PyCalc to do the calculation of phase diagrams. So we will send you information when they become ready. Okay, so now let me turn the podium to Brandon to start the next few hours ESPEI journey. Thank you.
All righty, thanks for coming, everyone. Glad that you're here. Let me share my screen. Okay, great. Yep, so this is day 2. Much like yesterday, this is supposed to be interactive, so at any time, including during the slides, feel free to stop me and ask questions. Also try and have the chat up in a separate window so I can try and keep track and respond to your questions there. Today is going to be quite similar to yesterday, so I'll have some slides here to introduce what ESPEI is pretty briefly, and then unlike yesterday, the pattern of today will be I'll show a couple of slides that'll talk a little bit about the theory side of things, since today is maybe a little bit new compared to some of the more traditional CalFAD things that we saw yesterday. So I'll show a couple slides, and then we'll have a demo in a Jupyter Notebook like yesterday, and then we'll repeat that for a total of 3 notebooks, and we'll take a break in between each notebook. So today I want to get started by talking about ESPEI, which is the database development and uncertainty quantification tool that's built on top of PyCalFAD that we talked about yesterday. So just to briefly review, again, we're interested in modeling now these Gibbs energies of individual phases by building up these Gibbs energy contributions. And again, we're doing that through fitting to the Gibbs energy derivatives and the phase boundary data. And so once we have those fits, we can then do all the interesting things that you saw yesterday. And we just repeat this process through the binaries, ternaries, and building up through multi-component systems. So again, we saw this yesterday. One of the challenges with database development is that you are trying to wrangle all this data and then transform it to whatever assessment format you have, then actually do the assessment and then publish it, and all the way through you're potentially losing some information about the historical aspects about the data or calculation that you're using. and so on. And this problem becomes, again, exacerbated when we realize we want to modify a description of a system that we already have. And so this is the problem that we're going to try to address through this software called ESPEI. And so I would say our first attempt at achieving this vision was started by Ziquei 10 years ago in sort of ESPEI 1.0 here in 2010. And so it was mainly based on Excel and this database-driven workflow that used ThermoCalc as the computational backend. But that one, of course, had some problems and wasn't very easy to generalize and extend. And so, of course, yesterday we saw that PyCalFed is a really great tool that is now completely open source. And so now we have our thermodynamics stack entirely outside of any commercial system, and we can develop new tools based on that. And so from that, we started sort of the new version of ESPEI. And so with this version, we have 3 goals. So we want to parameterize CalFed models from single phase data, and then use Markov chain Monte Carlo to optimize and quantify the uncertainty of those parameterized models. And then we want to propagate the uncertainty from Markov chain Monte Carlo to any observable property. And so we have 3 goals here, and so each of these will correspond to one of the 3 notebooks that we'll look at today. So first I want to talk about this parameterization step. And so like I said, we'll talk a little bit about sort of the theory about what's happening underlying this step, and then we'll go show an interactive example through the notebooks. Okay, so the goal is that, of course, we want to fit and parameterize the Gibbs energies, usually as a function of temperature and the internal degrees of freedom. And so maybe this comes from DFT, maybe it comes from experiments. But the key is that we know the internal degrees of freedom, or what the documentation, and we talk about it in ESPEI as non-equilibrium thermochemical data. But again, what that really means is that you just know the internal degrees of freedom. And so we want to fit this this data to both in temperature dependence and in composition dependence. And so for temperature dependence in parameter selection, we use the typical power expansion of the temperature, so fitting these coefficients A, B, C, D, and so on. And then in composition, we're using Redlich-Kister polynomials. So we get this composition dependence and then these interaction parameters, which are also potentially temperature dependent. But of course, one thing that we know from our experience is that if you have some amount of data, you can achieve better and better fits to that data just by introducing more parameters. But that leads to over-parameterization. And so it's illustrated here in this figure. And so the idea is that model complexity captures some amount or captures the number of parameters that you have, where model score captures the goodness of fit. And so again, this blue line here is just showing that intuitively we would expect that as we increase the number of parameters, we get a better and better fit. But in practice, that fit, of course, does not always extrapolate well. And so to try and find this trade-off and balance the trade-off between how good our fit is and the model complexity, we use this corrected Akiki information criterion, the AICC. And that's given by this relatively simple equation here. And so the idea is that the model score is this RSS, this sum of square residuals, and then we penalize that lowering the residual sum of squares by adding penalty terms for the number of parameters, and then this correction term here that penalizes the number of data points that you have. So if you don't have very much data, you also shouldn't be even more so, you shouldn't be adding more parameters. And so that's what this AICC tries to capture. And then just as a sort of motivating example for what this could look like is for this titanium vanadium system. So here we have two different cases where we provide a candidate model of 4 interaction parameters. And you can see that if we just take the maximum likelihood parameter selection, we are just trying to maximize the likelihood or minimize the sum of square residuals, and we would capture all 4 parameters that we use. But as you can see with this data, these 4 parameters aren't really giving us a whole lot of information or a very good fit for the number of parameters we're paying. And so maybe using 2 parameters, which the AICC selects for us, would be a better choice. And so you can see just visually that the lower number of parameters really qualitatively gives just as good of a fit to the data here as the 4 parameters. And so parameter selection is pretty simple. So with that, I want to go and talk about the demo for the system. And so a good time to ask any theoretical questions as we switch gears here. Okay. If there are none, we'll keep going. So if you go to workshop.mgfcloud.org, so the same spot as yesterday, it should remember you, but if not, you can log in again. And we're going into the workshop folder and then the ESPEI directory inside of that. So I can make it a little bigger. Great. Okay. Great. So we're going to start off with this this parameter selection notebook here, ESPEI parameter selection. And so again, the idea is that we're trying to start an assessment just from having data. And so what do we need for that? So we need 3 things. So we need first a JSON file that describes the phases and the models that will be assessed. We'll need all of the input data, which is documented here. And I'll talk about all these in detail in a second. And then last, you need a YAML file, which is describes the parameters that drive ESPEI and control all the file paths and hyperparameters that are that you can tune and play with. So again, first, we'll talk about the phase descriptions. So today we're going to look at a chrome nickel system. And so this is a pretty simple system, and it's obviously a binary system. And so I just want to mention up front that ESPEI can do systems with any number of components, and so it's written fully generally. And as I also mentioned yesterday, you can also use any model that you can use with PyCalFed, and you can control which model gets used on a phase-by-phase basis if you don't want to use the default one, if you wanted to use a custom one. Okay, and so for each phase, you need to specify 3 things. So the name of the phase, the sublattice model. And so this is a set of nested lists. So each sublist is a sublattice and all the components that can mix on that sublattice. So in this case, all 3 of these are just modeled with one single sublattice with chrome and nickel both mixing on them. And then the site ratios are the stoichiometric ratios of those sublattices. So in this case, there's 1 sublattice each, and so they have a ratio of 1. But if you had a different stoichiometry or a different sublattice model, this would correspond to, you'd have as many numbers here as you have sublattices. And so in all these notebooks, I've tried to link to the documentation. And so just as an example, you can go click, and the documentation is pretty comprehensive and pretty well documented. So there's a slightly different example on the website espei.org that walks through some aluminum nickel phases. So here you can see, for example, a case where more than 1 sublattice is used, and we specify the site ratios, and we can handle some symmetry with these equivalent sublattices. I won't talk about them today, but just know that that is a possibility. Okay. And so so that's the phase models files, the first thing. The second thing we need is all of the data files. And so there's 3 main categories of data that we can handle. So we can handle 1, the non-equilibrium thermochemical data. So again, As I mentioned, this is just where you know the site fractions. We can handle equilibrium thermochemical data and phase boundary data. So I have some examples here of each, and so we'll talk through them briefly. Again, these are all documented in the documentation. So the same page, if we're just scrolling down, we have some descriptions of the non-equilibrium thermochemical data, the equilibrium thermochemical data, and the phase diagram data. So all these are well described by the documentation. Okay, but I will still talk through them. So first, the non-equilibrium data. So we describe which components are in the system. Again, all the data can live together. And so each data is sort of a complete specification of what's in the data. So you can have, for example, chrome nickel and chrome iron data live in the same directory as JSON files. And then if you run ESPEI to only fit chrome nickel, it will just ignore the chrome iron data. And so that's the idea of why these are a little more verbose. So for non-equilibrium thermochemical data, we describe one phase at a time. So there's this phases that will always have just one phase name inside of it. And then we provide the information about the site ratio. So this should just be the same as what's in the phase models. And then we have these configurations here. And so the way the configurations work is that you have a list of different configurations of that sublattice model, or so which species are occupying which sublattices, and these correspond to the occupancies. So you can see I've lined up the configurations and occupancies. So in this case, we have 4 different configurations or compositions in this case, and so note that these all need to be in alphabetical order, and the documentation describes that. But yeah, we have 4 different compositions here, one with 10% chrome, another sample at 10% chrome. So these would be like 2 independent measurements or calculations, and then one at 40% chrome and another one at 40% chrome. And so then we provide the conditions. So we're at 1 atmosphere and 1583 Kelvin. So again, these are all the same units as pKalFed. So all SI units. Energies are all in joules per mole atom or joules per K mole atom, depending on the type of data. And so in this case, we have these 4 different measurements that correspond to these 4 different configurations. And so you'll notice that the values here is a nested in 3 levels of this array, right? And the reason for that is that the data sets can do broadcasting. And so if you have 4 measurements and 2 temperatures, then this will be a 1 pressure by 2 temperature by 4 different configurations. And so they broadcast against each other. And so that's really useful if you have, for example, DFT data that's on a grid of occupancies, and you have temperatures and possibly also pressures. You can include them all in the values in one large dense array. And so it's really nice and compact, like I said, if you're coming from DFT data. If you're coming from experiments, which is what this is, it's converted from an experiment from Watson in 1995. Then a lot of times you won't use that broadcasting feature, and you just have this 1 by 1 by 3 array. Okay, so that's the non-equilibrium thermochemical data. And the other one we'll use today is the phase boundary data. And so the form of this is very similar. So we have our components. For the phase boundary data, we include all the phases that participate in the equilibria. So in the particular set of data that we have here. So in this case, there's BCC and FCC. These should all be FCC A1 and BCC A2. So you'll have to excuse that. They're a little out of date here, but the actual data sets that we'll use are correct. And so similarly, these broadcast against each other. So here we have 5 different temperatures and 1 pressure. And instead of now compositions, we have values. And so I'll talk more about the phase boundary data in a little bit as part of what these actually mean and how they fit in. But actually for parameter selection, we don't use the phase boundary data at all because we're just interested in using this non-equilibrium thermochemical data to generate the parameters. Because of course you can't infer anything about the parameters directly based on phase boundary data. And that's the whole challenge that we're trying to solve. Okay, so that's a brief overview of what the data looks like. And then finally, you need this YAML file that drives ESPEI. So really, this is what maybe a minimal YAML file would look like. And so you need to describe and point to the file of the phases file. So for example, phases.json. You need to point to the directory that contains all of your data set. So these JSON files, where the phase models is this one, sorry. And then you can control the verbosity of the output just by integers and the database name that it writes to. And then for parameter generation, these are the sort of minimal set of parameters to describe parameter generation. So first, which XS model you use. So we only support the linear one right now. So you're locked to that choice, but then you can provide the reference state. And so we provide this SGT91 reference state. And so that one uses the SGT unary data. SGT91 is just sort of a legacy name that refers to the paper in 1991 by Dinsdale. But we use actually the latest unaries, so that it would be version 5. And so like I said, this is the most basic input YAML file that you could use to drive ESPEI. And again, all of this is documented on the website. And so we have this ESPEI YAML input files documentation page that contains all the different parameters that you can use for the parameter generation and the MCMC steps. And so you can go and look through this page and read in detail what all of these, what kind of values all of these take in some examples. And so one key thing that I wanted to point out is that the SGT91 is the default reference state. But you can write your own reference state if you want to switch out the different unary lattice stabilities that you use. So like I said, we use the SGT lattice stabilities for compatibility, but you can provide your own as well if you're interested in developing your own, or you can let ESPEI fit them for you. Again, using that power expansion and temperature that I showed in the slides. Okay, so let's actually get started running the code and actually running this fitting. So code-wise, it's pretty straightforward. We're doing some imports, and the key function that we're trying to import here and run from the notebook is this run ESPEI function. And so everything is kind of encapsulated through this run ESPEI function. And so in the second cell, we're going to load from this generate param settings.yaml file. So again, we're describing the parameters in a dictionary or in a YAML file, which gets loaded to a dictionary. So in this case, we have our three phases in our chrome nickel phases.json, which is in our directory here. We have our data sets directory, which is called input data. So that corresponds to this input data. And as you can see here, you can have all the data in one spot simultaneously, and you can even have data for phases that aren't going to be stable or aren't going to be modeled, like I mentioned, and they'll just get ignored properly. And you can organize these individual JSON files any way that you like. Okay. And then we apply some tags here. And so the tags are a really interesting feature that we have. So you can tag individual data sets and then apply different parameters to them, like weighting. And so I'll talk about that a little bit more in a bit, but just for example, we can see that if we go and look at some of this estimated entropy data, you can, it's, I think, easiest, by the way, to look at these JSON files if you open with instead of JSON, open with editor. And now you can see what this file actually looks like. So this one's a little bit messy because it's automatically generated, but you can see that we have this extra field tags here, again, discussed in the documentation. But one of the tags is that we estimated the entropy. And so in the input file, we want to weight all the data sets that are tagged with estimated entropy with a weight of a factor of 10. And so that's an example of using that. And so, of course, what we want to do, like I said, is we describe it in that YAML file, and then we load it. And so it gets loaded just into a dictionary. And so you could create and modify this here on the fly. And then to actually run ESPEI using this file as described, we can just run the cell. I will clear all the output quickly so we can start fresh. Okay. All right, so if we run ESPEI with this level of verbosity, it'll just tell us that it's fitting all three of our phases, and pretty simple. So you can see that it starts and finishes in just a couple seconds, which is very typical for parameter selection. So that's one of the main reasons that we want to use it, is it's very fast to generate the parameters starting only from this single phase data. And so using what we learned yesterday, we can go ahead and define the components, phases, and conditions for a binary phase diagram and plot that. And so this also will take just a couple seconds. And so here's the phase diagram from the generated parameters. So you can see also, as we discussed yesterday, you can't quite see this really narrow phase boundary, but it is there. Okay, so if you don't know what chrome nickel looks like, you might be wondering, well, is this any good? And if you do know, then I won't spoil the surprise. But we can plot, just for comparison, plot all of our phase boundary data on top of this phase diagram to see what it looks like. And so here I'm running binplot, so plotting the phase diagram, and then ESPEI provides this data plot function. So you can see that it doesn't take a database, but instead it takes the same components, phases, and conditions, and it takes your data sets that we loaded from the input data. And so now if we plot the phase diagram with the data on top of it as symbols, you can see that ooh, yikes, it maybe isn't that good. Maybe decent on the BCC side, much too low solubility. And you can see that we have this region of BCC stability here, right? And so again, I just want to emphasize that these parameters were selected without considering this phase boundary data. So just considering some of the input thermochemical data that we'll talk about in a second. But, and again, this is just supposed to be a starting point for MCMC optimization, which I'll talk about in the next notebook. Okay, so now,
Brandon, before you move on there, when you say parameter selection, do you mean you're actually coming up with the like model expression for the energy, Gibbs energy?
correct. Yeah, so we're starting just from the, so only from this, these different sublattice models and the data. And so starting from that, we are constructing a TDB file of all of these parameters. And so I can actually show, so the output database is this generated TDB. So if you're running this alongside me, you should have a generated .tdb by running that parameter generation step. And so if we just double click and open and look at it, this is what we'll see. And so you'll see some functions here. So these are all lattice stabilities from the SGTE 91 data set. And then ESPEI defines these functions with VV and some number, just ordered from 0 to however many parameters you have. And so if we scroll down, we can see that Again, the pure elements are just defined by the lattice stabilities in this case. And then we have all the interaction parameters that we fit. And so these are all what ESPEI fits just based on only those sublattice models and the data, and using this corrected Akiki information criterion. And so as you can see here, and this is leads right into where I was going, you have 4 BCC interaction parameters, 2 FCC interaction parameters, and 3 liquid. So we're going to take a look and see if that makes any sense. Where was I? Okay, yeah. So we had just plotted the phase diagram using these generated parameters against our phase boundary data. And so again, using what we learned yesterday, we can just do a calculate over all the phases at 1500 K, and then plot the Gibbs energy surface. And so we can see just from the surface that we have 3 phases here: the FCC, BCC, and liquid. And to me, the FCC and in blue and the liquid in green look pretty reasonable, but there's this kind of strange wiggle, I think strange, in the BCC. And so, yeah, let's take a look at that and what parameters are fit. So ESPEI provides this plot interaction function that lets you, as it says, plot the interactions. So you can provide the database components and one phase at a time. And then you have this configuration, which is the particular interaction or configuration that you want to look at. And so for a single sublattice, it's pretty straightforward. If you have more than one sublattice, you can look at any individual end member or configuration that you like. But then you provide the property and the data sets, and you can plot the interactions that were fit. And so for BCC, this was the interaction parameter that are fit for the enthalpy of mixing. So you can see that on the area where we have some experiments, it's pretty good and pretty well fit. I have some estimated points here in the triangles, and you can see that those are definitely less well fit. And we have this this well here around 65% nickel that corresponds to this minima in the energy surface. And so that's kind of weird, right? And so let's keep that in the back of our mind as we just check all the other parameters and see that they're reasonable. So FCC, again, just using these two sets of experimental data, to me this looks pretty reasonable, and then the liquid as well. And so just by eye, again, based on these 2 different experiments, this looks pretty reasonable. Maybe we have some an extra parameter that we don't need, because this looks pretty parabolic to me. And if we look back at the TDB, we can see that there's 3 composition-dependent access parameters. And so maybe there's a little bit of overfitting there. And so so we'll talk about tuning that in a second, but just another way to see this. So I opened up the TDB file here to look at the parameters that ESPEI generated, but you can also access the database directly using this query syntax that Richard talked about yesterday in the custom model example. And so you can actually just query these any way you want. And you can see that if you query for excess parameters of the BCC phase, we get 4 of them. So the same 4 that show up in the TDB, this is how they're represented here. And so you can see that we have the 4 with parameter order 0, 1, 2, and 3, and then the expressions for them. So we have these VV006 plus VV0005 times T, and so on. And so just to maybe format that a little more nicely, we can say that the L0 interaction for BCC is the VV0006 parameter plus the value of the 0005 parameter times T. And so the key thing here is that all these functions, these function lines in your TDB correspond to values in the symbols of the database. And so you can look them up and modify them, which we'll use later. Okay, so again, so this is the same plot as before. we're looking at the BCC, and we can see that maybe our intuition or just by eye, this looks overfit, and it needs a little help to be nudged in the right direction, right? We as modelers can clearly see what the algorithm cannot, and ESPEI, we have designed it to be really a tool for you to use in modeling, and to be able to put in your intuition about what the parameters should look like if you have some. And so in this case, what we're going to use is this AICC penalty factor parameter. And so again, this is all documented in the documentation. I won't click there this time, but it's that same page. And so the idea here is that we can add some additional penalty on top of the AICC and additionally penalize the factors. So again, just briefly, looking back at this equation, the number of parameters is k. And so by tuning this penalty factor, we're tuning the factor of k that shows up in these 4 different spots, and providing a additional penalty to increasing k by the number you provide here. And so we give you the ability to adjust this penalty factor for individual phases and for different types of data that you can provide. So the enthalpy of mixing or formation data and the entropy of mixing or formation, you can modify them this way. And so for BCC, like I said, this is just it's pretty good up here, but I think just needs a little nudge to not overfit and have this strange wiggle here, right? And so we just give a small AICC penalty factor of 2. And then the liquid, we want to give it a more forceful nudge, because we think, again, if we scroll up, that, again, this looks pretty parabolic to me. And so maybe 3 parameters that we got in our TDB are not necessary. And so this file or this YAML file matches what's in your ESPEI directory. And so you'll see that all the parameters are the same. And so all we've done from the last time is just add this AICC penalty factor. And then so we can load that file, that YAML file, into a dictionary, and then run ESPEI again, now with these new penalty factors. And so now what that returns is, again, this database, this new database that we created from the data and the sublattice model descriptions. And so we can, again, programmatically query the number of parameters. And so now we can see that we only got 2, whereas before, when we queried the parameters, we had 4 interaction parameters. And so we can show here that we are, just by giving a little bit of nudge and penalty, that we can reduce the number of parameters. And so now if we do the same plot interaction, where instead of using our old database, we use the new one with the penalty factor, we can see that we have still a lower energy dip here, but much less weird wiggle that we had last time. So again, we can plot the energy surface, and you can see that there's still a little bit of a hump, but it's much more reasonable compared to what the FCC and liquid look like. And so if we again plot the phase diagrams, we're going to plot both of them to compare to each other. So this is what we started with without the penalty factor, and then on the bottom here we have the penalty factor. And so you can see maybe it's a little better. It's debatable. It's still not great. But again, I want to emphasize and drive home that again, this is only fit on the data that you provide here. So in these different interaction parameters for the enthalpy and entropy. And so given only that, I think this is a fairly reasonable starting point for doing some further optimization. And so that's what the whole next section is about, is the Markov chain Monte Carlo. And so before we move on, I want to give an opportunity again to ask more questions on how the parameter selection works. So yeah, any questions so far?
Kind of a side question outside of what we're discussing here, but has any consideration been made in kind of making energy equations kind of obey any kind of known higher level physical equations that we might know would describe a certain type of quantity?
Yeah. So in parameter selection, not really. I think it's pretty rigid. In terms, so we really in parameter selection as it exists today, it really only supports Redlich-Kissler interaction parameters, and it's just doing a very basic power expansion fit on the data that you provide. So these were all interactions today, but you can also fit n members again to that power expansion in temperature. However, I would say that I think this philosophy that we have about using the AICC and the statistical approach to parameterization, you can definitely apply to different, more physically correct parameterizations, like the low temperature Einstein model. And we actually have a paper where we did something similar for different unaries. And so, yeah, we think the philosophy is valuable and has been applied to other systems, but ESPEI itself does not do that. That being said, yeah, go ahead.
I was hoping to maybe add a little bit onto that if you've.
Sure.
We have done a little bit of research, not necessarily into making the parameters obey some sort of physical like constraint directly, but we have done some what I would call preliminary research into building physically motivated priors based on families of systems. And so this was something that I did with Axel van der Waal a couple years ago, where we basically did like a statistical analysis of published TDB files and collected them based on like the chemical family that they were in to try. We focused on the liquid phase and basically trying to figure out kind of if there's a tendency for different interaction parameters to fall in a distribution. And I would say we found some evidence for that, but we haven't taken it any further than that. But it's definitely would be possible to do that sort of analysis and then use the results of that with ESPEI.
Yeah, thanks.
Yeah, definitely. And I think the power of the parameter selection is really just to provide a starting point for the Markov chain Monte Carlo. And I think for me, philosophically, it's sort of grown to be built and be much more flexible. So for example, you can actually specify your priors in the MCMC simulation. And so if you know what a more physically correct model looks like, and you know what your parameterization looks like, then you could put your priors into that. And we'll talk a little bit more about that in the next section. Okay. Any other questions on parameter selection? Okay. Well, I did promise a short break between, so that was the first of our 3 notebooks. And so let's go ahead and take a, let's see, it's 10:46. So let's say about almost 15-minute break. So we'll start at the top of the hour. So that's 11 a.m. Eastern time. So let's go ahead and take a break, and I'll see you all in about 13 minutes. Thanks. Welcome back, everybody. Let me go ahead and share again. So again, following the similar pattern, I will show a few slides, and then we'll do another demo, and then take another short break. So in the last section, we talked about the parameterization of calculated models from only this non-equilibrium single phase data. And so now we want to talk about the Markov chain Monte Carlo, which is, relatively speaking, is much more general in what you can optimize and what you can use, and also allows you to quantify the uncertainty, which is very unique. As far as I know, ESPEI is the only user tool that lets you do this for CalFed today. And so, and for that reason, I want to talk a little bit about what Markov chain Monte Carlo is, and the theory behind it, just so that everyone is up to speed and we can speak the same language. And so the goal of Bayesian parameter estimation is to compute this posterior probability distribution of some set of parameters conditioned on the data that you have, D. And so we do that by what's called Bayes' theorem here, or Bayes' rule, is that we take our likelihood times our prior, and we normalize that with what people call the data. And so visually what that looks like for just some hypothetical 2-parameter theta1, theta2 system is we have some prior. And so this, as you can see from the is just only a probability distribution that's a function on the parameters. And so this, the idea of the prior is to capture the experience of the modeler or the information that you know about the parameters. And so in this case, with these 2 parameters, the prior is that they're just follow some uncorrelated Gaussian-like distribution. And then the likelihood now, now that you've observed some data D, you want to be able to compute what the probability of observing that data would be at all the different sets of parameters. And so again, visually, that looks like this, where we have this, again, 2-parameter system. And we're able to compute what the probability is at each point in this parameter space. And so the 3D version of that looks like this. And then finally, the posterior is just computing them, is multiplying these 2 probabilities together. And so you'll notice that I didn't include the data in here. So in practice, being able to compute this probability would mean that you have to observe all possible data that exist. And this integral it's an integral and very hard to evaluate in practice. And so really what we're interested in is the proportionality of the posterior being proportional to the likelihood times the prior. So that's what is visually shown here and what we'll talk about. And so again, doing this this overall parameter space, especially in high dimensions for all the data that you have, is very expensive. And so that's where Markov chain Monte Carlo comes in. And so the idea is that we want to sample from this parameter space and compute the probabilities and construct a Markov chain where that is just a sequence of independent samples of parameter space. Again, doing that sampling by Monte Carlo. And the whole idea of this theory is that the probability of observing some set of values is proportional to the number of times it appears in the Markov chain. And so using this as an example, if we have the set of parameters theta1 equals 0.7 and theta2 equals 0.3, and we're at this maximum in the posterior, that set of parameters and parameters in this local region are going to appear much more frequently in the Markov chain that we construct than something out at 0.1, right, which is very low probability. And so that's the core idea of what we're trying to accomplish in Markov chain Monte Carlo. And so the key thing that we have to define is the likelihood function, which we have one likelihood for each type of data, and then we multiply those probabilities by each other. And you can also provide a prior, and ESPEI lets you do both of these things. But there are some other considerations that we need to take into account. For example, in CalFad, we know just from our knowledge of the form of these parameters that there can be some correlations. And so in this example, just imagine that this 2-parameter space, theta1 and theta2, theta1 and theta2 might be coefficients in some excess parameter that's modeled as L equals A plus BT. And so we know that maybe in this case, the optimal highest likelihood is at 1/2, 1/2. But we know that since the linear combination of these, there might be some most likely energies that they're going to have some correlation between each other. And so in traditional Markov chain Monte Carlo, these different correlations and scaling and things that show up in your parameters is something you have to tune manually. But in ESPEI, we use a different method called ensemble Markov chain Monte Carlo, which constructs an ensemble of samples of this parameter space, and then you make new proposals by scaling to the ensemble. And so for an example, if we started this blue point here, if we were to just take a random step in the parameter space in like you would in traditional Markov chain Monte Carlo, you might take a step out that way or a step out that way, but both of those would be very low probability of being accepted. Those would be very, very bad steps and wasteful because, again, the idea is that we want to construct this Markov chain where the higher probability parameters are in the chain more frequently. And so we really want to sample this space. And so what ensemble Markov chain Monte Carlo does is it stores a sampling of a certain number of chains of MCMC Markov chains in this space. And then when you take a new proposal, you scale that proposal depending on the state of all of the other chains. And so we generate this ensemble by default by taking whatever database you provide. So maybe it comes from parameter generation, maybe it doesn't. But we generate the ensemble by taking a normal distribution, uncorrelated normal distribution centered on the initial parameter value with a width of the standard deviation of some factor of that value. So we choose 10% just by default. And then for you can provide a wider initial ensemble, and that samples this parameter space more widely, or a narrow one, and that's a tunable parameter that we'll talk about. I see Ursula has her hand raised, so you can go ahead with your question.
Yes, I have a question. With the correlation between parameters, Kubashevsky had a rule that you have a certain ratio between enthalpy and entropy. Can you also still introduce that kind of to help the algorithm along? And then eventually when the algorithm sees it's no longer needed, that it abandons it?
Yeah, that's a good question. So actually my suggestion would be to use that rule to inform your parameter selection and inform your, if you have to, like, if you don't have data, for example, for like the entropy of mixing, you can use a rule like that. Actually, I do this quite often because it's very useful to generate initial parameters, and then in the correlation that will be sort of built in, or it will find the correlation automatically, and just having a good starting point can get you there. I think it's probably not necessary to like put in these correlations from the beginning, and it's actually, I think, very difficult to do in the general case. And so I think the beauty of the ensemble method is that it can find these correlations for you and take them into account automatically. Thanks for your question. Okay. So yeah, we use ensemble MCMC to try and combat this correlation and take more efficient samples and not waste time selecting from a low probability space. And so the last thing I want to touch on before we switch gears on the theory side is that the likelihood functions. And so for thermochemical data, I think the likelihood functions are kind of obvious in that you are just trying to match some observed value of maybe the enthalpy of formation to the one predicted by your parameters. And so you can just define the likelihood function as the maximum likelihood square difference between the observed and predicted value. But for phase boundary data, it's actually more complicated than that. Because often for phase boundary data, you really just know maybe the temperature and compositions of phases in equilibrium. And so we have to do something a little bit different here. And so what ESPEI does is you take as data the conditions that describe an equilibrium, so temperature and pressure, and then you provide the phase compositions of the phases that you observed in equilibrium. And so, so what's in these plots is two hypothetical phases, a beta in yellow and alpha in blue. And the provided data is, and so this is at some fixed temperature and pressure. And so the provided data is that you know the phase composition of alpha and the phase composition of beta. So really, these are on some, you don't necessarily know what the energies are when you're making this observation, but just for simplicity and to guide the eye, I've just plotted the observed phase compositions on the energy of these energy surfaces. So these are, again, some surfaces with some proposed set of parameters, and we're trying to evaluate the likelihood that these set of parameters match these phase boundary data. Okay, and so the way we do that is sort of a two-step approach. So first, at each phase composition, we compute a global minimum hyperplane at each composition, temperature and pressure. And so what that looks like is here, there's this dashed line of the hyperplane for the alpha phase, so all phases in equilibrium at this composition. And we do the same thing. We compute the global minimum energy and hyperplane for all phases in equilibrium at this composition here. And so we get this hyperplane, which is inside. And so this composition for the set of parameters is inside this miscibility gap. And so we get this corresponding hyperplane. And so then we define the target hyperplane as the mean of the chemical potentials of all the different vertices hyperplanes. And so that's the solid line. And so that's the first step, is determining this target hyperplane. And then the second step is we want to compute the likelihood. And so that is the driving force of these constrained single phase energies to the hyperplane. And so you can see that for this case here, there is some driving force. And so in the limit of convergence, the hyperplane here will have 0 driving force. And so these points should match up, and these energy curves should give local minima on the hyperplane at the phase compositions described. And so I'll show a little bit about what that looks like in data in the interactive part, but just as a motivating example, a couple of years ago, when we were first developing this iteration of ESPEI, we were looking at the copper magnesium system. And so this diagram here on the left is the single phase generated phase diagram based only on the thermochemical data, again plotted with the phase boundary data, just so that you can see, get an idea of how good the agreement is or how not good the agreement is. And so if we perform the Markov chain Monte Carlo optimization and look at how the negative likelihood converges, and so in this case, the negative likelihood is plotted, and so decreasing means that you're increasing your total likelihood. And so there's two phases here. There's this burn-in phase, which we'll talk more about later. But basically what's happening here is you have your starting point parameters, and those have very low likelihoods. And then as you are optimizing, the likelihood will increase and then start to level out. And so once you are, the likelihood isn't decreasing much, then you start doing some, you enter this uncertainty quantification phase where you're sampling the probability, the posterior probability in the neighborhood of whatever the mode or modes are of your parameters. So if you do this for copper magnesium, you can get this phase diagram at the end, according to our work in 2019. So you can see that that again here the agreement is much better. And so with that, if there's not any questions here, I will go ahead and transition into the demo. Okay. All right. So we're back at our Jupyter Lab interface. And so we can open up the ESPEI MCMC notebook here. And so I wrote these so that they're self-contained. And so you didn't necessarily have to run the parameter selection before the MCMC, although in practice, that's probably what it would look like. And so to get started, all you need is a database. So in this example, a TDB file. And so you can start an MCMC run from any database that you have. So regardless of whether or not it came from parameter selection in ESPEI, or if you're taking an existing database that you want to modify, or some existing assessment that you want to continue or to extend in ESPEI. And so the mechanism for how that works is this is the starting database that we'll use here. So this is the same one that we generated from the AICC penalty factor. And so what ESPEI looks for is just that whatever functions or database symbols, if we think back to the programmatic way, have names starting with VV and then followed by some number. And so those are variables that are optimized. And so this, again, is where a lot of the generality comes in to the MCMC optimization, because the MCMC doesn't really know that this VV002 parameter corresponds to this temperature-dependent parameter of this temperature-dependent variable of this interaction parameter. It just knows that this value is a parameter that I can adjust, and I can only, from the perspective of the Monte Carlo sampler, it only sees what the effect is on the likelihood function. So I think I mentioned yesterday that one of the areas of development that we have is to extend PyCalFAD to handle the quadruplet approximation quasi-chemical model. And so in terms of ESPEI, all you have to do is provide the variables and degrees of freedom that you want to fit. And then it doesn't matter what the parameters look like and how you use those, because PyCalFAD knows how to compute all the observables, so the enthalpies of mixing or the equilibrium set of faces. And so this is where really the power comes in. And so all the examples here today with chrome nickel and most of the work we've done in the past has all been for Gibbs energy related parameters, but you could easily use this framework to use a custom property model. And all you have to do is define that model in PyCalFAD, like we did for the viscosity model yesterday. And then you define a corresponding likelihood function for that particular type of data. And that's all you have to do in ESPEI, and you can use any model. So yeah, that's what that looks like. Again, I think the key takeaway from this is that you can bring your own TDB, and you don't have to use the one from parameter selection. And parameter selection, again, in my opinion, really exists to serve the MCMC, as that's, I think, really the powerful part of ESPEI. Okay, and so in this case, again, this is sort of the simplest YAML file that you can have that drives MCMC. So again, we define the system output and some of the MCMC parameters. But this is the one that we're using here. So again, this is using the same information with the tags that we used before. So this is where those tags really come into play here, is that so you can weight any of your data sets individually in the file. Actually, I'm not sure off the top of my head if I have them. If I have any weighted ones in this data set, maybe not. But you can provide the weight as just an entry in the file. So again, I'll open in an editor. And so this is what a little bit cleaner file looks like. So if you were to weight this individual data set, it would just look something like this. And so if you have a weight of 1, that's the default. And so this would basically be a no op here. And so weights greater than 1, you are making that data more important. And what you're doing in effect by adjusting the weight is you're adjusting the inverse of the standard deviation of this data. So we define the likelihood function for every piece of data as a normal distribution. So we assume the residuals are normally distributed, so centered at 0 with some standard deviation that depends on the data type. And so we provide some like default standard deviations. So like for enthalpy of formation, the default for enthalpy type data is that the standard deviation is 1 kilojoule. So that's the like error bar that we assume. And so by providing a weight, you're adjusting that. And so if you were to take a weight of 10, that would say that the standard deviation of that data, instead of being 1 kilojoule, would be 1/10 times a kilojoule. So that would be 100 joules. So that's what the weights do. And so, so again, the promise of the tagging system is that you can weight data sets individually. You can provide these data weights here, so you can weight an entire class of data. So like ZPF is the phase boundary data. So you can provide a weight to that class of data, or you can use this tag system, and any data set that you tag with estimated entropy gets a weight of 0.1 applied. Or I also use that here for any data that's tagged DFT. I also want to weight that less compared to like experiments. And so I provide that weight here. Okay. I guess while we're here, this is probably the best time to mention this excluded model contributions tag as well. You probably saw for the parameter selection. And so what this means is that Richard showed yesterday a little bit of how custom models work and how models are constructed. And so there are contributions to the model. And so one of them is ideal mixing, or ID mix. And so this name is specific to that model. And so what this says is that if I have DFT data, I want to exclude the Gibbs energy contributions from ideal mixing when I'm doing the fitting, because when you do a DFT calculation of you know, maybe an SQS structure, that energy that you get back doesn't include a contribution from ideal mixing, nor does it include a contribution for the magnetic entropy in the way that we would do it in CalFed. And so when you're fitting Gibbs energy models that have these contributions, you want to exclude those from that data. So the DFT data won't affect how the magnetic parameters are fit. Okay. We have a question from Ursula.
Yes, with the magnetic, it's my understanding is if you have spin polarized DFT calculations, you have a magnetic contribution to the energy. If you have non-spin polarized calculations, it doesn't mean anything if the stable phase is actually magnetic.
Yeah, so for this one, what this is excluding is the CalFed type TC and BMAG parameters. And so the interpretation of this is that if you were to do a finite temperature DFT calculation, even if you have spin polarization, you can't capture the magnetic ordering energy, right? Like you wouldn't capture the discontinuity in the heat capacity for FCC nickel if you did a DFT calculation. And so what this is doing is making it so that you aren't fitting any contributions from that when you do that calculation.
But the problem is, and we have been struggling with that, is that when you have like a phase and the reference states, for example, take something with iron or cobalt, the HSER value actually corresponds to the paramagnetic state. So you really need to reduce everything for the non-magnetic Gibbs energy to the paramagnetic one. And you get the magnetic moment from the DFT calculations. The issue is the Curie temperature, because that is not a trivial issue to do it with first principles. So what we did for our estimates, and I admit it's extremely crude, but it's the best we can do without the further first principle calculations, is just use the ratio between magnetic moment and Curie temperature for the stable experimental magnetism that we know, and then use the DFT magnetic moment to estimate a Curie temperature. But to me, it's just kind of swiping it off the table, I think is a bit dangerous. That's all what I was trying to say. I don't have a perfect solution how to overcome that problem, but I think it's something that should be addressed eventually.
Yeah, I definitely agree. And so if you did some approach like that, then the energy that you predicted, so the tag DFT here is really just a name. So you could name it, Brandon's way of doing DFT, or, Ursula-DFT. And so if in the way that I do DFT and I have used the data, there's no magnetic entropy, because we don't use that kind of approximation or any higher level theory that would allow you to capture that magnetic entropy. So I exclude it here. But if the data that you had from the calculations that you described did somehow estimate the magnetic contribution to the energy, then you would just change this and not include the magnetic part. And so that would be equally valid. It just depends on what data you have and what contributions are included in that one. And like I said, the way that I do DFT, even with the spin polarization, you aren't really capturing the CalFad magnetic parameters, which is really modeling the magnetic entropy. So the spin polarization doesn't give you that part.
And that's where I'm struggling. It's not only the entropy, you also have a contribution to the enthalpy. And
Yeah.
I think of DFT more in terms of enthalpy rather than entropy.
Yeah. Yeah, so thanks. That was a good discussion. I think hopefully for the audience clarified how you would use these.
I'm sorry if I sidetracked, and after all, we have only a handful of magnetic elements. So for most systems, it's actually not that relevant, but I'm sorry if I said.
No, do not apologize. It's a great point, and definitely something to emphasize here. So in our, I guess my philosophy and approach here is that ESPEI should allow you to be very flexible in choosing to exclude different types of contributions if those aren't in your data. But by default, it's to include all of them, right? And so, for example, experimentally, if you had experimental data, you would never exclude these, right? Because an experiment has everything, right? And so yeah, I think that was a valuable tangent, even if it was a little tangent. Okay. So yeah, so I mentioned the excluded model contributions, and so this is what our input file looks like for the MCMC here. And so one thing I want to note is that the outputs from a MCMC run are not only the database with the optimal parameters plugged in, so just some TDB file, but you also get out this trace file. So that's the, I'll talk about more in a minute, the sets of parameters that in the Markov chain, and then the probability file is the array of posterior probabilities that match up to the the proposals. And so in this case, they're both set to null just for this example. So we don't write them out to files, but we'll still get the objects to be able to manipulate them. And again, I'll talk more about it in a second. So again, we're following the same pattern as in the parameter selection. And so we're importing primarily this run ESPEI function, loading our MCMC settings, which again just look exactly the same as the one I just showed. And then we are running ESPEI. And so I'm going to go ahead and start this now because this will take a couple of minutes. So this one is only running 3 iterations, and it's running them in serial, so not parallelized, because we're all sharing these resources on this cloud infrastructure. But ESPEI can be parallelized, and so you do that through the scheduler argument. And so null just means don't do parallelization. And again, all this stuff is in the documentation on espei.org. And so, so yesterday, I think I forgot to mention this for parameter selection, but we get this red box of output here. And so yesterday, all the red boxes were warnings, but this is just how the Jupyter Notebook displays the logging output. And so for parameter selection, it was pretty brief for the verbosity that we had. But I did want to turn up the verbosity a little bit here. So it's set to 2 in our output. So we can see a little bit more detail, and I can talk through a little bit what you see. Since when you're actually doing ESPEI fitting, this is sort of how you're going to monitor how things are progressing, how long it's taking, what everything is sort of looking like. And really, this is this log file that we're printing out to the console here is where you're going to go to start debugging anything. So I'll talk a little bit about that here. And so we have some initial startup stuff up through about this point. We're gathering data, and then you can see that it's going to this this loop here, and starts to follow this pattern. And so just to break it down, here's what's happening. And so you are making a proposal of a set of parameters, and then we compute the likelihood of that proposal. And so it just tells you the time it takes to do that call to the likelihood function for all the data. And then it tells you for each type of data what the contribution to the log likelihood was. And so we operate in log space because then you can add all the numbers, and they're reasonably sized, where if you were to work in probability space without the log, you would be multiplying a bunch of small numbers with each other and you'd lose precision. So everything is in log space. So the log likelihood for the non-equilibrium thermochemical data is about 1100 here. We're not using equilibrium thermochemical data, so it's 0 for this case. And then the phase boundary data likelihood is about 65,000. And so again, these are all log probabilities, so we can just sum them. And so the total likelihood is 66,000. And so these numbers, in a sense, don't really mean anything. They're just likelihoods. And so for your system, it depends on the amount of data. So if you have more data, your likelihood might be bigger, and if you have less data, it might be smaller. If you change the weights, that's going to change the likelihoods. So don't read into this too much. But we do provide a probability for the initial set of parameters. So whatever TDB you provide ESPEI, it will compute the likelihood for that. So you can see that the likelihood is minus 72,000, and then you add the log likelihood with the log prior. In this case, we're not using a prior, and so the log prior is 0 in this case. And so the total posterior log probability is the same as the likelihood. And so we compute the initial one. And so anytime your likelihood increases, the Markov chain Monte Carlo algorithm will accept that proposal. So the process is, again, make a proposal, compute the likelihood. If the likelihood increases, then accept that set of parameters. if the likelihood decreases, then sometimes you accept and sometimes you reject. And you do that in vanilla MCMC, you do that by the Metropolis algorithm. And with the ensemble, it's basically the same thing. And so by taking that step back, that's what's making this Markov chain Monte Carlo algorithm consider the uncertainty and explore the parameter space. If you were just going forward, you would just have a hill climbing algorithm, which is not that useful. Okay. And so you can see here that we're running, and so it tracks all of the, you'll get this 1 of 3, so we're running 3 iterations. So this is completing the first iteration. And it also gives you the acceptance ratios, the cumulative acceptance ratios. So one thing I didn't mention here is that in our TDB file, we had 10 parameters. So this was our starting point, right? We have 0 through 9 parameters, so we have 10. And so part of the ensemble algorithm, the ensemble MCMC algorithm, is that you have to have at least a factor of 2 chains times the number of parameters. And so for 10 parameters, we have to have at least 20 chains. But often it's useful to do more than that. So the default in ESPEI is to do 2 chains per parameter, which is the minimum number. But you can increase them as much as you like. Again, this is all documented. And so this just uses 2 chains per parameter. And so you can see that we have initializing 20 chains with 2 chains per parameter. So what that means is that you have to evaluate the posterior probability of all 20 chains, and then you can decide whether to accept them or not. And so that's this array here. So we can see, like, for the first chain did not accept the proposal, and the second one did, and did not, and so on. And then after the second iteration, again, these are cumulative acceptance ratios for that chain. And so we can see that in the second one, we rejected, and then here we accepted, and then we did 1 accept, 1 reject. So a 50% acceptance ratio, or 1/2. So like I said, we're just doing this for 3 iterations, and then the MCMC is complete. And so this, I think, completed a few minutes ago, but if you're following along, you may have noticed that it probably took probably like three-ish minutes to do this. And so, I mean, we're just computing the likelihood, it takes about 1.2-ish seconds. And we need to compute that 3 times 20 chains, so 60 times. So about a minute plus some overhead and startup time and so on. And so at the end, it'll just tell you, like, here were the value of the initial parameters, and here's the values of the optimal ones after. So optimal being whatever set of parameters had the highest probability. And then it'll just tell you the change as a fraction of the initial parameters, which is just a helpful diagnostic at best, I think. And so again, what you get back is you get back the database, and you get this trace. MC calls them chains, so we access it through the chain. But most people, I think, refer to it as the trace. And then you get the log probability back. And so you get those back as just arrays. And so if we look at the shape of those arrays, you see that we have the trace has 3 dimensions. So you have 20 chains times 3 iterations, and then you have 10 parameters. So this is the parameter values for every set of proposals in the Markov chain. And then the log probability is just the number of chains times the number of iterations. So we have 60 total probabilities for every 60 sets of parameters in the Markov chain. So that's what that looks like. And so if we just look at what we got after that, I can clear all the output after this one runs. So this is what we started with. So I loaded up the starting point database, and so just to remind you, so we had this still BCC being too stable, and then let me just clear the, or don't want to clear now. And so if we compare to the after 3 iterations, you can see it's a little bit better. So we're starting to move the Gibbs energy higher for BCC on the nickel rich side, and starting to move that single phase BCC region over to where it should be. And so this is just 3 iterations. So I wouldn't expect this to be fully converged to assessment quality diagram, right? And so for the sake of time in our compute resources, I went ahead and did this out of band. And so on my old laptop, 2015 MacBook Pro on 6 cores, I was able to do 40 chains, so 4 chains per parameter, and 1,000 iterations parallelized over 6 CPUs in about 3.5 hours. And so again, 3.5 hours may seem like a long time, but you know, that's basically the you push go and then you walk away and get a coffee or go to a great workshop like this one, and then you come back and your simulation is done. Okay, and so I'm going to go ahead, and so I saved those files as NumPy arrays. So they're these binary.mpy files, and so these are what are saved if you enter. If we look back at the settings, if you enter values for this trace file and prob file, these are file names that get created when you run MCMC. So just for the demo, I didn't make them, but you should all have these in your directory. And so you can see that there's this chrome nickel trace, chrome nickel ln prob.mpy. And so we can load these arrays and print their shapes. And so you can see that there is what I said. And so there's 40 chains and 1,000 parameters in each. Okay, and so now we can look at the convergence again. So this is looking at how the probability changes with the number of iterations. And so this is kind of like what we saw in the slides, but I was nice enough to give you a zoomed in version here. And so one thing to note is in the slides, we plotted the negative log probability, but from here on, everything is positive. So increasing probability is moving towards the mode or towards the optimal set of parameters. So if we zoom in a little bit, you can see that it has this asymptotic like convergence and onto some probability value. So maybe for this one, just zoomed in, maybe after 600, 800 iterations, we're like starting to become converged. There's lots of actually convergence literature out there and lots of diagnostics. So I don't think I have a lot of time to talk about them today, but definitely something to look into if you're interested in using ESPEI in the future and quantifying whether or not you're actually converged or estimating how many samples you have to take to be converged. There's lots of metrics out there. And so again, we can use these. One thing I didn't mention is that one line on all these plots are one individual chain. And so I mentioned we're doing 40 chains in parallel, right? And we're doing 40 chains in parallel. And each line corresponds to one of those chains. And so if we look at the plot here, we can plot how individual parameters are corresponding. So I'm just providing some index in that array. So if we take the 0th parameter, we can see how that one changes as a function of iterations and how it gets closer to converging, maybe around 600, 800 or so. And yeah, that's how the convergence looks for the different parameters. And so you can see that the starting point that we generated at iteration 0 is centered maybe around positive 35,000. And then we, as I mentioned in the slides, we initialized the ensemble just by taking a normal distribution, sampling from a normal distribution centered at the initial value with a standard deviation of 10% of the initial value. So in this case, the starting point was maybe 35,000. And we initialized the ensemble of 40 chains by taking a normal sampling with a standard deviation of 3,500 around 35,000. So you can see also if we switch to a different parameter, this is, I think, one of the temperature dependent ones. So maybe the mean was about 11 for this particular parameter. And so we sample, and then the chains sort of quickly find some higher probability space. And then as they all sort of evolve together, they'll get closer and closer to a mode. And you'll find as you get closer to a mode and closer to optimum, they should have this effect where they kind of spread out. And so this is where, again, they're trying to examine, or they're trying to sample the probability space of the they're trying to sample the likelihoods of the parameter space. So if you see your parameters kind of walk together up and down, that usually means you're not converged yet. You should really have this like nice like fuzzy mixing between the parameters. So if you like follow maybe like one particular color that sticks out to you, like this blue sticks out to me, you can see that it tends to wander, and that's the kind of behavior that you want, is you want them all to be well mixed. Okay. And so we can then just take again the optimal set of parameters from this 1,000 iterations now. So before we plotted just after 3 iterations, and if we plot the 1,000, we can see that the agreement is much better and quite good in this case. So this is after 1,000. I saw a message that not everyone has all the files up to date, and so part of this, I think, is just caused by some of them getting added after yesterday, so between yesterday and today.
Brandon,
Mm-hmm.
if you could, for the people that don't look like they have all of the files up to date, could you just show them right now how to stop their Jupyter server and then start it again?
Sure, but if they
if they left the window open overnight, they wouldn't have gotten the new changes pulled in.
Okay, I think if you look at the if you change some of the files from yesterday, it could also mess with it, but you should just be able to I don't know, I haven't done this, Richard. Is it just log
It's
out?
the hub control panel.
Okay. Oops, not print. Yeah, so if you go to File, Hub Control Panel, you should be able to stop. We'll do this real time.
Yeah, it should take maybe like 20-30 seconds to stop, and then maybe another minute to start again. Oh, now you can start it again.
Yep. And so this should repull. It should pull everything in again, as long as you didn't modify them yesterday. And if you did modify them yesterday, then I do have some steps that we can do, but I can maybe show that during the break, which is coming up. So that was actually the end of the notebook. Is that the agreement now with Markov chain Monte Carlo, like we saw for the copper magnesium example in the slides, is much better. And so with that, I will take any questions on anything up to now. So any of the Markov chain Monte Carlo and doing the optimization, doing this uncertainty quantification part. Yeah, I'll take any questions, and then we'll take a break. And also during that break, I will show how to update your notebooks if that restart didn't help you. So I'll take questions now.
May I ask a question about databases or like input data for ESPEI?
Sure.
With the new equilibrium driver of Bicalfat, for me, an error appeared with ZBF data, which was saying that at least one set of points is within the target tolerance. So I had like really close ZBF points. and I got then this error message. Like, what does it mean? Or
Yeah, okay, I can explain that. So the way that so that's part of the multi-phase calculation. And so we need to compute these for this example, in the beta phase, this data is inside of a miscibility gap. And what we want to compute is this Gibbs energy on the phase inside the miscibility gap. So we need to not have global minimization. And so for that, we use kind of the same tricks as Richard showed yesterday for local equilibrium inside of ESPEI to generate a starting point automatically that's close to this composition. And then we use that as the starting point for a local equilibrium calculation so that we can not do the global minimization and not get the miscibility gap. And so the error that you saw is basically saying that the way we construct that starting point is we take like a random sample of the energy surface. So again, kind of the point sampling pictures that Richard showed yesterday. And then you try to find some points that are close to your prescribed phase composition. And if you can't find a point that's close enough, then you get that error. And so it's probably easiest just for, that's not very easy to control from outside, but it's like a one-line change in the software to like make that tolerance a little wider for your case. So you can just
thanks.
Yeah, email me or reach us on Gitter. I'll have the contact.
Like I tried to split up my data set into 2 data sets, so then it didn't give me an error.
Okay.
Yeah, thanks.
Yep, you're welcome. And the slides, I don't think they're in the repository yet, but after the workshop today, I will make a PDF export of these, and they will also be in the GitHub repository. So thanks for reminding me to upload these.
Another,
Go ahead.
Another kind of slightly unrelated question. We can save this one for later if you think it's more appropriate, but just wanted to, it could also be just a conversation starter, but get people's thoughts and yours in particular on kind of the reevaluation of parameters, kind of the parameter form during this process, because obviously this is only for one representation of those parameters, one set of parameter and variables that you're varying at a time.
Yeah, that's a good point. Yeah, we can definitely talk more later. I would say my take on that now, if just to get people thinking before we get on the break here, is that this Monte Carlo optimization, like you said, would be for one set of parameters, right? One parameterization as ascribed by this TDB. And so the way my suggestion would be that if you want to compare different parameterizations, different models, anything, right? You just do 2 or more ESPEI Markov chain Monte Carlo runs, and then you can evaluate the uncertainty. And then for whatever your metric is, right? Whatever your observable is, maybe it's a particular like phase boundary of interest, or maybe your data. There's like well-defined statistical techniques for how to take the Bayesian quantified uncertainty and compare 2 models to each other. So similar to the Kiki information criterion that we used in parameter selection, there's a Bayes information criterion that I think has been published on by Raimundo's group a couple of years ago, where in their model fusion approach, they use the Bayes information criterion to be able to compare different parameterizations against each other for some observable. And so my take on that would be, that's how I would use ESPEI, is a tool to do that forward quantification of different parameterizations. And then I can use something sort of outside of ESPEI, like the Bayes information criterion, to compare my models against each other and decide which is best.
Sounds great to me.
Okay, I'll give one more chance for everyone to ask a question. Okay, hearing none, let's go ahead and take another, let's say 17-minute break. So come back at quarter after, and that'll give a couple extra minutes for me to show really quick how to update your files here in case that update didn't work for you. And so if you have all the files like this trace.mpy, then you're good to go on break, and we'll see you in about 16 minutes. And if not, I'll take 1 or 2 minutes here to show that really quick. Okay, so I did anticipate this, but I moved my file. There we go. Okay. So basically it looks like this. And I can do this in real time really quick after I explain it, and then put this back up. But basically you want to create a new launcher and go to the terminal application instead of a Python. And so if you don't have a launcher open, clicking this little plus button will make one. And then you want to go to, in the terminal that comes up, go to the workshop directory. So if you're starting from here, it's just cd workshop. And then you want to run this git stash -a ---espei, and then git pull. So I'll show that really quick. And then I'll put that slide back up once you've seen me do it in real time. So you can go back to your home folder by clicking the folder, and then plus to get a new launcher. If you have an existing one, that's fine too, doesn't matter. And then click the terminal, and then run those commands. Again, I'm just run them here really quick, and then I'll put the slide back up that has the commands on them. If my terminal will start. I don't know if anyone else is running into this issue, but the terminal is not starting. But anyway, if it does start, again, you can just go to the workshop directory, git stash, git pull. And again, you only need to do this if you don't have the same versions of the files that we've been running today. So like this Chrome nickel trace.npy, if you don't have that. And that restart the file hub control panel didn't work either. Okay, with that, I will also go take a break. So I'll see everyone at quarter after. I will just leave this up in presentation mode. just after, a quarter after. So I'll go ahead and start the third round. Let me start sharing or start the recording. Great. Okay, so the first two sections and notebooks were really about the behavior and how to use ESPEI itself. While this third part will be about how to take the parameters that ESPEI optimized and computed and quantified the uncertainty for, and to be able to visualize that uncertainty a little bit and propagate it. So this will be relatively brief, but I do want to show again a couple slides of how that's done, and then I think I just have 2 or 3 quick plot examples of how that all gets put together. Okay, so first, how to actually do uncertainty propagation, or what does that even mean, right? And so as an output from our Markov chain Monte Carlo simulation, we have the traces. So we have proposals in our Markov chains for every chain as part of the simulation. And so we've taken these parameters, and now we've sampled and converged around parameter space for them. And so to quantify the uncertainty and propagate it, all we have to do is plug in parameters from Markov chains into PyCalFat, into our TDB, and then do the forward simulation to compute any observable of interest. And then we can put error bars on that property. And so here's one example from our paper in 2019, where we did this in copper magnesium and computed the liquid enthalpy of mixing and propagated that to the equilibrium property. And so one question that you may ask is, well, which parameters do I use? And so you can use all of them, but in practice, what you probably want to do is take some highest density interval, or HDI, of your parameters. And so again, if you think about what you get from Markov chain Monte Carlo is you get samples from, here's 3 different distributions. You get samples from this entire distribution, right? And some of your samples may be part of some long tail of low probability space, but maybe that's not useful for your problem as far as the uncertainty that you want to quantify or you want to propagate, right? And so that's where we construct these highest density intervals. And so what that means in practice is that, again, we have all the samples, all the posterior probabilities, and we just take the 95% of our data, of our samples that have the highest likelihood. And so doing this is sort of the Bayesian equivalent of confidence intervals in frequentist statistics, right? And maybe you have a 1 standard deviation confidence interval or a 2 standard deviation. Well, the Bayesian equivalent is basically these 95% HDIs. And again, the one of the nice things about these is that they're defined numerically, and so you don't have to have a particular distribution that you're sampling from, like you would if you were to define a model. Is that yeah, we can do them numerically. And so one thing to note is that even if your data is multimodal, then the highest density interval region, so these gray regions, could span multiple modes. And so in your CalFat assessment and your CalFat uncertainty quantification, if you were to find a solution that had multiple modes, then the 95% or this HDI method of doing uncertainty propagation would still capture that. And so one interesting thing here is the actual value here and what 95% means. I think we're still trying to figure out as a community. This is still very early on in how to actually do this analysis. And the meaning of this of 95% HCIs and the width of your predictions is going to be tied to the width of your posterior distributions. And in turn, that comes from the weights and the uncertainties of the data and your priors, right? So there was a little bit of discussion in the chat about during the break about how to handle this, and Richard mentioned that determining the weights is something that you can do precisely from error propagation analysis. So I think for what I want to say, and the take home here is, for this to be really truly meaningful, is that you need to have very well defined uncertainties in your data, and therefore you need to weight things correctly. And that's a part of being able to have actual meaning, physical meaning in this highest density interval. So that's a really key part. And again, if you've spent a lot of time around CalFAD and done CalFAD modeling, you know that collecting the data and critically evaluating it is an extremely important part. And I think this just shows that for the uncertainty analysis, even more so, to have a physical and interpretable uncertainty analysis, even more so is it important to critically evaluate your data. Okay, so that being said, this is how you choose parameters from your trace, is by using these highest density intervals. And so again, just to give an idea of what it means to propagate, is that these might be the enthalpy of mixings of different liquid parameters. And so notice that the parameter scales on the y-axis aren't all sharing the same scale. But so the uncertainty quantification tells you basically one parameter at a time, and here's what you get if you marginalize the uncertainty for that individual parameter in this case. But of course, often we're interested in propagating those. So it's as simple as summing all the different proposals and marginalizing over your quantity of interest. And so again, really the beautiful part is that you can do this not only on thermodynamic properties, but anything that you can compute with PyCalFAD, you can put an error bar on or put some uncertainty ranges on. And so we just have some examples here of visualizing the Gibbs energies of these are all for metastable FCC and liquid copper magnesium. And so looking at the Gibbs energies, or looking at the solidus and liquidus phase compositions, phase boundaries for the solid liquid metastable FCC. And so we've taken the phase diagram here. I'll talk about it a little more after the demo, but plotting the uncertainty of the phase boundaries. Here we've plotted the uncertainty in the phase fractions at a particular composition of magnesium. And then here is just another way to visualize this diagram here, where we can look at the probability of some amount of liquid being stable. Okay. And so with that, like I said, I'll show a quick demo of a couple examples for this particular system that we've been working on. Okay. So I'm going to go to the ESPEI UQ notebook. And so this one is very similar. So again, as I mentioned, the last two is really like what ESPEI does, and then the uncertainty quantification and propagation is then like what you can do with the outputs from ESPEI, or really any Bayesian approach. Even if you don't use ESPEI, you could still use this approach in principle. So just in this first cell here, I'm just going to import all the things that we're going to use, load our database. Here I'm loading the one from the starting point. We're going to substitute the parameters in this out, the values out later. And so it's perfectly fine to have the starting point database. And then we're going to load up the data sets for comparison and the trace and log probability arrays, and just extract the symbols that we're going to fit, or that were fit. So all these VV, some number that's stored in this variable. Okay, I'll quickly clear the outputs. Okay, And so the first thing I want to show is just some example of like uncertainty quantification. And so what I mean when I distinguish quantification versus propagation is, to me, quantification is visualizing at the level of a parameter what the uncertainty is, or quantifying numerically what the uncertainty of a parameter is. And then propagation is anything that marginalizes over some sets of parameters, or computes some observable based on the parameters. And so that's the distinction there. So here, this is just a form of uncertainty quantification where we're trying to visualize the form of the parameters. And so this figure is kind of big. And so one trick that we can do to visualize it a little easier is if you right click, you can go to this create new view for output. And so that will create this new window here, which doesn't maybe seem to make it any better, but that would allow you to right click and get your browser window, and you can open in new tab. And so if we do that, a new tab will open up that will just have this figure. And you can also like save from here and whatnot, but just a Jupyter trick. And so now we can see this, this figure in its entirety. And so I've plotted up, so this is called a corner plot. And so along the diagonal of the corner plot, you have histograms for each individual parameter that's labeled here on the x-axis. So this one is the L1 chrome nickel interaction for BCC, and this is in particular, this is the temperature dependent coefficient, and this is the temperature independent coefficient in this column for that same interaction parameter. And so so this histogram again is the L1 temperature independent term for the BCC phase. And so everywhere below the diagonal is where is the correlations between the two different parameters. And so you can see that some of these are relatively uncorrelated, but a fair number of them are pretty strongly correlated. And again, this shouldn't be that surprising to anyone who's done some CalFed modeling. For example, that the temperature independence coefficient of the same interaction parameter is strongly correlated with the temperature dependent one. That shouldn't be surprising to any of us, that this is what you may see in some of your assessments. And again, motivating the use of ensemble method, whereas if you were to try and sample this with a method that didn't consider the correlation, you would waste a lot of computational time. And so this can give you some ideas of just what the parameter values look like. So just looking at the histograms and what their relative widths are to each other of the different parameters. So you can see like this L1 term, you know, is roughly bounded by, like, maybe you can't see very well, is by from -10 to -15, and so about 5. And the L0 term has roughly the same range from about -1 to -3. And so you can do that kind of visual analysis just from these corner plots. I think they're nice, and it may be motivating to areas where your parameters might be overspecified or underspecified if there's some coupling between them. Okay. So that's a corner plot, pretty straightforward. Now here's a simple example of propagating the uncertainty to the enthalpy of mixing. So there's a little more code here, so I'll talk through that while we set up the calculation. So in the corner plot, by the way, we just plotted all the parameters after 600 iterations burn in. So if you recall back to the MCMC, you know, roughly 600 iterations, maybe later, is where I would say that you start to converge based on the log probability. But again, for like real uncertainty analysis, you'd want to be more rigorous than, you know, maybe 600. But we'll just use that here for simplicity. And so for this case, we just want to, again, we're calling back to the parameter selection. We saw that we wanted to use our Akiki information criterion penalty factor to nudge the solution and nudge the number of parameters towards two interaction parameters instead of 4. And so that's why we want to look at it here, just to see what the actual uncertainty turned out to be for the set of weights and data that we used here. So basically, just like I described in the slides, it's pretty simple. All you are really doing is you are taking some highest density of parameters. And so in this case, this little helper function that I wrote here is inside this UQ helpers. And basically all it does is it takes in your trace and your log probability, and it takes a credible interval, so width of your highest density interval of, and the default is 0.95. So you'll do 95% highest density intervals, but you can tune that with this function. And then you choose how many iterations you want to consider as burn-in. So again, we're just going to choose the first 600 where we just discard those parameters because it's not converged yet. And then there's this parameter called thin. And so when you even when you by throwing away the burn-in, we have 400 iterations times 40 chains. That's how many, so 1600. Sorry, 16,000 total parameter proposals, and that's a lot of proposals to compute by PyCalFat, and it takes some time. So we can thin them, and so it's just take every 200th proposed parameter and plot that. And so basically what's happening here is we're doing a loop over all the parameters in this 95% highest density interval, taking every 200th. And then we're creating a dictionary of parameters, and then passing that dictionary of parameters to equilibrium. And so once we compute that equilibrium, we're adding it just to this list. And so we're constructing a list of equilibrium results of those X-array functions that we talked about yesterday. That's what's in this EQ results. So we can check the last one maybe. And so yeah, this is just the equilibrium X-array for the property that we computed. And this is just for one particular set of parameters. And so what this chunk of code does here is it will take all of those different parameters and concatenate them into a new dimension called samples. And so if we look at the dimensions here, they're the same ones that we had yesterday for a binary system, right? You have dimensions of NPT. This is a step calculation in nickel composition, 2 components, maximum 2 internal degrees of freedom, and 3 vertices. And so if we do the same thing for this new variable EQ uncertainty propagation results, you can see that we have all the same ones, except now we have this new samples dimension. And so I've concatenated all of the samples of from the Markov chain, so after the burn-in, after the thinning, and concatenated them all together. And so now all of these arrays of properties now also have a dimension called samples. And so then we can do interesting things with them, right? We can plot them, visualize them, compute statistics on them. But just in this example, we can then compute the uncertainty bounds on BCC enthalpy of mixing. And so this one is pretty interesting. So one thing I want to mention up front, just about the general trend, is that you can see that the uncertainties go to 0 at the endpoints. And that shouldn't be surprising because we started with fixed lattice stabilities from the SGTE unary data. But if you were to have any degrees of freedom, so again, those VV functions in your TDB file in your unaries, you would also be able to quantify the unary or lattice stability uncertainties. So whether you provided your own or whether you want to take some existing ones and add the VV parameters to optimize them, you could. But like I said, here they're fixed in this particular analysis, so the uncertainty will always be 0 at the endpoints. So interesting here is that this is chrome nickel, right? So on the left side we have chrome, and we can see that there's very little uncertainty on the chrome rich side of BCC. And if we think for just a second, we'll realize that, well, that's because BCC is stable there, right? And we have this all this phase boundary data that describes what the BCC should look like. And that's even where our experimental data is, right, is for the measurements on the BCC rich side. And so you can see as BCC becomes more and more metastable in practice, that the uncertainty gets wider and wider. And so you can see that there are, you know, wider uncertainty bounds on the side where we just had those estimates, right? If we look back at our parameter selection data for BCC with this parameterization, you can see that we just had these two estimates here on the nickel-rich side for BCC. And so, of course, the uncertainty on that side will be wider as well. And so this is something that you can quantify with ESPEI. And so finally, the last brief example I'll show here is the phase fraction versus temperature. So again, we'll compute it. So, you know, really it's the same pattern though. You're taking a highest density sample of your parameters. So this will be the same as in the last example, but we're just redefining a different set of conditions. And now we want to consider all the phases in this system at the same time. And we'll do a step calculation in temperature at fixed nickel composition. And so again, you can see that, that we can have our equilibrium uncertainty propagation results. I didn't mention, maybe it's clear, but we also compute the optimal parameters. So the parameters that have the highest likelihood, just so that we can plot these like solid lines of what the optimal database would look like. Okay, so yeah, we can look again at this EQ uncertainty propagation result. You can see that our thin was a little higher this time, and so we have fewer samples. But again, this is for the thinned 95% highest density interval. And so then we can compute that again, and you can see that you can hardly see any uncertainty, right? So if we zoom in a little bit to the center region, we can see that there's a little bit here. And I would argue that that this is much smaller than you might see in the other example, maybe what you would have guessed, or by what you would have guessed from seeing this figure right from the slides. So I would argue that this actually shows up partially because of two things. One, the amount of data available for these phases, which wasn't available for FCC, copper, magnesium. And second is that if you go back and look at the weight that we used for the phase boundary data, we gave it a much higher weight. And so that weight concentrated the posterior probabilities much more than in that copper magnesium analysis. And so all of the phase boundary data is heavily weighted. And so anything that has to do with equilibrium, phase stability, or regions of energy parameter space close to stability are going to have a lot lower relative uncertainty. And so that's what we see here as compared to the other examples. Okay, and so that concludes this small section. Before I open it up explicitly for questions and discussion, I did have a couple more slides just to give some ideas and talk about some of the other things we're working about, but I didn't get to show here. So one of the things I did briefly allude to is that we can also, you could apply this same methodology and compute phase diagrams where you have propagated the parameters and plotted the phase boundaries, and you can visualize qualitatively what the uncertainty on the phase diagrams look like. And so that work and this work on doing some of the propagation for copper magnesium was led by Noah Paulson and Marius Stan at Argonne National Lab. And they developed the PDUC phase diagram uncertainty quantification package, which is available, and you can visit this link and download it and install it. But I think really the takeaway from that I want you to pull from the examples is that really all of these are just loops over parameters, and your creativity in how to visualize them. PDUQ has some nice code that makes visualizing the phase diagram very easy, and also has some nice defaults for the visualization if you don't want to do that work yourself. So that's my pitch for PDUC. And then finally, the last thing I wanted to touch on this uncertainty propagation and quantification side is some work from last year on doing sensitivity calculations based on the outputs from ESPEI. And so sensitivity is really a measure of how the likelihood depends on the parameters, or the derivative of the likelihood with respect to the parameters. And so in this paper, we did some analysis for actually this chrome nickel system where we looked at the sensitivity sliced up and marginalized in different ways. And so this one is sort of the basic view of what is the sensitivity as the MCMC simulation proceeds, of how the of individual parameters and coefficients. So again, these are the same ones that we've been looking at before, just with different phase labels and slightly different labels. But that's something that you can do if you can access the derivative of the likelihood. And what Richard developed in the work mathematically is how you actually do that, in particular for the phase diagram data with the method that we touched on before. And then this one is just another example of slicing that same data up, but marginalizing instead over particular data sets instead of parameters. So this one is looking at, if you marginalize all the phase regions from a particular set of data, what's the sensitivity per equilibria of that data set. And so you can sort of start comparing across data sets and see which ones give the most marginal information, right? So this topmost blue curve is giving you the most sensitivity or the most information per phase region or per phase equilibria data point. And so it's a really interesting way that you can imagine how to flip this on its head, right? Instead of computing the sensitivity of data you already have, you might compute, might try to predict, if I added new data here, how much would that change my uncertainty? And that's the kind of questions that you can ask and answer if you have the sensitivity data. And so finally, I just want to end then with a little bit of contact information. Again, these are going to be, these slides will be uploaded as PDFs after the workshop today to the GitHub repository, so they will be available. And finally, yeah, thanks for all of us on behalf of the Materials Genome Foundation in the workshop. And so I want to use the rest of this time for anyone to ask any larger questions. And then after that, we will close it out. So the floor is open.
Okay, let's see if we don't have any questions, comments. Again, I want to thank you for your participation. I want to thank Richard and Brandon for the well-organized presentations. I want to thank IBM for their support. We'll see you next time. If you have any questions, please reach out to us. Thank you.
Thanks for attending, everyone.
Yes, thank you very much to everyone.
I want to mention that Eternal is just we have Eternal papers project already. So Eternal is doable too. Hopefully in the future we can have Eternal sessions too. Great. Thanks, Brandon and Richard.
Bye.
Thank you, Fabio.
Bye. Thank you.